We have mostly Chinese on the names here, so let's see if we can read it.
Yeah, they are my parents.
Okay. Good to meet you.
Hi, Jacob.
Hey,
We were just waiting for Dinesh.
Okay.
Other say it. Up here.
Hi.
All right, Dan, it looks like we have the whole committee here, so if you want to take it started
Yes,
with preliminaries, you're
so
welcome.
Mark is there in the room. I can't see who's in the
Yep,
room.
we have Mark in the room, I'm here, and Dinesh is here, and then online we have you and Pratik and Jacob, so we've got the whole committee advisor.
So I guess we can start. So we've convened here to attend the defense of you. The protocol is kind of standard. He's going to give a presentation of 50 minutes or so. And we can try to keep our questions during the talk to clarification questions. There's going to be opportunities to ask him questions later and give the whole forum an opportunity to ask some questions before the committee can convene. Even though we scheduled it for 2 hours, we can try to finish it earlier in 1 hour and a half, which is common. And other than that, Mark, do you want to say anything before we start?
maybe just a little bit. So we kind of like got Yue from a non-CS background maybe 5 years ago. It was like quite surprising, but like quickly Yue got up to speed. And so it's been doing really interesting empirical work in language and vision. Really kind of like the best results in many places. And so just kind of excited to see him go off to bigger, better soon. So yeah.
Okay, go ahead then, Yue.
Okay, thank you. Thanks everyone for coming to my defense. It's not a good weather and multiple conference deadlines, and so we really appreciate you attend this defense. So in this talk, I will just give an overview over my past 5 years, which I try to incorporate language priors from large language models to enhance visual intelligence. Okay, so my research goal is to build visual intelligence that can benefit the real world. And one concrete example always motivate myself is in Botswana, an African country, there are only 15 radiologists, but there are over 2 million people there, and over 2,000 patients will die for TB each year, a disease which can be diagnosed from chest X-rays. If we can apply AI systems to assist in this diagnosis of such disease, we can actually save a lot of human lives. But can we trust existing AI systems to deploy them in these critical domains? We've seen great success of deep networks in general domains. They can help us write code, write a summary, a lot of many other tasks. They achieve this by scaling up the data. But in critical domains like healthcare or robotics, it is more challenging to obtain such high quality data, and sometimes it contains biases. And since we train a big neural network, it's function like a black box and lack of transparency, we may end up having a limited generalization ability in those black box models. Here are some concrete examples. So during COVID-19, people are trying to build chest X-ray classifiers to diagnose COVID. And they can grab some training data in hospital A, like a developed country, as the domain training data, and they want to test it for auto domain, like another hospital in developing country. They found those COVID-19 detector can achieve nearly perfect performance in hospital A, but it will decrease a lot when applying into a different hospital. And when you visualize models' attention maps, they found models are not looking at the lung area, but looking at some like corner area of the X-ray. This is because those hospitals, they use different symbols to distinguish healthy and COVID patients. And models are relying on those spurious correlations as shortcuts to achieve high performance. So compared to how medical professionals making diagnose, they will leverage knowledge priors they learn from textbooks, like looking at the airway, looking at the lung area. They rely on knowledge priors to make more robust diagnosis. So AI systems is lacking of such reliable priors to make robust deployment. Another example is in the robotics domains, where we try to build general purpose agents that can not only navigate in residential environments like living room, bedroom, but also we can apply them in diverse environments like gym, daycare center, etc. However, existing data sets for training such agent is mainly focused on residential environments like Proxol. And if we try to train agent on Proxol and apply them in novel things, it can achieve very high performance on residential, but get nearly to random performance when applied to novel environments like gym. So if we can find a way to incorporate prior knowledge, like gym usually has treadmills typically arranged in rows, we can help the robot better generalize in those unseen scenarios. So this thesis is motivated by this hypothesis because language and vision represent the same physical world. From a real physical world entity, we can get the 2D image representation to train your vision model, and we can get the textual descriptions to train a language model. And the recent success of large language models, we scaling up our training data on internet text. We can build very high performance large language models which encode a lot of word knowledge. And we hypothesize whether we can incorporate those textual priors to enhance our vision system. So how to apply those language priors? In this thesis, I mainly explore two different ways. First, we use language as model structure. Because language is human readable, it's explicit, we will use it as part of model structures to make systems more interpretable. And second direction is from the data. And we will try to show how can we use the language data, the knowledge we learned from language data to help synthesize visual data to improve the data efficiency of some vision tasks. So the thesis statement, in this thesis, we try to incorporate language priors into model structure and data synthesis process. And we try to enhance the interpretability, robustness, and data efficiency of visual intelligence. So for this talk, I will talk about two groups of work. First is using language as model structure, specifically using language as this bottleneck structure, try to improve the interpretability of image classifiers. And we further show that such bottleneck structure can help us to incorporate knowledge priors from medical documents to build a more reliable medical image classifier. In the second group of work, we will show how can we use language models to help synthesize visual data to improve the data efficiency in embodied AI and vision language models. And let's start with interpretability. So the efforts try to improve the interpretability of black box models is mainly focused on post hoc methods, which we won't change the architecture of those models because they are very important for models' performance, but rather incorporate another black box module. For example, like this GradCam module, which will backpropagate the gradients into the image to visualize models' attentions. So we can visualize models' attentions when predict the class to be a chickadee, but if you change the class to an irrelevant label like coffee maker, it still highlights the similar area. It's hard for human to distinguish the differences between those two different predictions. So usually those post hoc methods will give you not very faithful explanations, and sometimes they can be misleading. So the alternative method is called inherently interpretable method. And what we'll talk about today is concept bottleneck model. And we will change the black box architecture and insert a human annotated concepts layer. So those concepts are just a list of attributes. So they are human readable and interpretable. So we will project the input image into those human readable concepts and use those intermediate predictions to the linear layer to make a final label. So we can obtain local explanations by looking at those concept scores. We can know which concepts are more important for this input image. And we can also get global explanations after we train this linear layer. Because from the linear layer, we can know the association between class and concepts to understand which concepts are more important to classify this class. However, there are some challenges to scale up the application of concept bottleneck models. First is how to ask a human to annotate. It requires extensive human efforts to annotate those concepts. And second, previous work shows those interpretable method has worse performance than black box. To address those challenges, we propose this language model guided concept bottleneck. So we, instead of asking human to annotate concepts, we will prompt a large language model to generate those concepts. So we can simply using class names in our prompts to generate descriptive sentences which are related to this class. And we can use those language generated concepts to automate the construction of bottleneck. And then we can use a image text alignment model, which is clip to ground the image and text. And then we can use a linear layer to make the final label prediction. So this framework is quite flexible, which means we can apply it into any image classification tasks. And we evaluate this on diverse classification data sets, including common objects, fine-grained objects, human action recognition, textures, skin tumors, and satellite photos. So we found our language bottleneck is competitive with their black box counterparts. So our baseline is linear probe, and the main difference between linear probe and our method is we incorporate another bottleneck layer, which improves the interpretability of our system. And the results on few-shot and fully supervised performance on those data sets found, we found our language bottleneck can achieve higher performance at fewer shot, and we can get competitive performance with more training data.
Is this on the cup data set, the 200?
Yeah, it's average over the 11 data sets.
And does it give any benefit over the pre-annotated, like the attributes that already come in the birds data set?
Yeah, we have comparison with other baselines using human annotated, and we found we can achieve better performance.
I see.
So, so we can see like our model is more data efficient. We don't need a lot of data to achieve higher performance because we can get benefits from language priors. And here are some qualitative examples to show the interpretability. So we grab the top 3 concepts for each class, and the top 3 concepts is ranked by their weights in the linear layer, which denotes their importance for classifying such objects. And we find they are quite aligned with human judgment. So to summarize, in this work, we show we can automate the construction of language bottlenecks using large language models, and we can achieve competitive performance as black box models. So one motivation we start this project is we try to apply such interpretable models in critical domains like healthcare. But there are some other challenges before we directly apply bottlenecks. So first is compared to general domain, the data in medical is much smaller in scale and sometimes contains biases. They are unevenly distributed over populations. And second, we also found the architectures we designed for general domain may not have sufficient priors for how to processing medical images. We will have evidence to show that. And all those lead to existing systems very sensitive to domain shifts, making them hard to deploy in real world. So we need more robust models. In the next work, I will show the knowledge bottleneck, which we try to apply the knowledge priors from medical documents into medical image analysis. So how to test the robustness of systems? We usually use these confounded data sets where we try to incorporate confounding factors like sex here, and we build the disparate distributions between training and validation and test. So for in-domain, we will confound the positive cases with female, negative case with male. But during test time, we will just switch this combination to build an adversarial out-of-domain distribution. So a reliable, robust medical image classifier will not use sex as the feature, but rather learn how to classify positive and negative cases. And we can build other confounding data sets like using age or race as confounding factors. And we compute the performance of vision transformer, which is a black box on such data sets. We found they can achieve very high performance for in-domain, but it will drop a lot for out-of-domain, which means they mainly learn how to use confounding factors as features to classify those, to achieve high performance in those data sets. Another problem is in the model architecture, and previous work have already showed those deep vision backbones have good priors for processing natural images, like images of cat. We can prove that by doing these experiments. We have a baseline, which just using pixels as features, and there's no priors. And through a linear layer, doing linear probe to do the classification. And we can also grab deep vision backbones like CNN and WIT. To be noticed, they are untrained. Using them as featureizer to get the features through a linear layer to make the prediction. We find on natural images like images from ImageNet, they can outperform pixels, which means even those networks are totally untrained, they still have good architectural priors on how to processing natural images. However, for medical images like chest X-rays and skin lesion images, we found CNN and WIT, they are not better than pixels, which means those architectures do not have good structure priors on how to processing those medical images. And without the guidance of appropriate priors, those models can only learn from the data to form the solution. And we know medical data can be small scale and biased. The models may just rely on those spurious correlations to form the solution. And this will cause catastrophic failures. So how can we incorporate more priors? Our method is inspired by how medical students are trained. So medical students will first stay in the medical schools to learn some clinical knowledge from textbooks. And then they will send to hospitals to do the residency and practice on some real cases. Previous method skip the first step and only rely on the data to learn the model, to build the model. And we will try to incorporate the first stage, and we want to get priors from medical documents. So how can we get medical knowledge priors from medical documents? We use this retrieval augmented method. For example, we want to learn how to classify COVID, and we will find some medical corpus like PubMed, which contains a lot of medical articles. We will use this query to retrieve relevant documents, using the retrieved documents as context to summarize concepts. Using this way, we can find diverse and reliable concepts, because we can always look at those documents to verify the faithfulness of those concepts. So with those concepts we discovered from medical documents, we can again apply the bottleneck architecture, and we get our knowledge priors from medical documents, and we ground them using some fine-tuned grounding functions. Through a linear layer, we can make an interpretable classification. We found using this way, we can achieve better robustness. So compared to vision transformer, we compute the average performance on 10 confounded data sets across chest X-rays and skin lesion images. So we found vision transformers, they can achieve high performance for in-domain, but it will drop a lot for out-of-domain. But for our knowledge bottlenecks, we sacrifice a bit for in-domain, but achieve much higher out-of-domain performance, which achieve a better trade-off across different domains, and we can obtain better robustness. So in this work, I think it's a good answer to the question about why we need interpretable models. If a model can achieve very high performance, but why we need the interpretability? And in this work, we provide a good evidence that interpretable structures can help us to incorporate knowledge priors from literature, and it can achieve better robustness in those medical domains. Another recent work I want to show
clarification. So you motivated that this requires kind of like the specialized knowledge corpus, etc., right? So did you actually validate that kind of assumption of the work that if you just asked an LLM?
Yeah, good question. We applied this in our paper. We compared directly prompt language models without using documents. We also compare with some other knowledge resources, like we found PubMed achieve the best performance because it can connect comprehensive medical articles.
And do you think that it remains the case now, or is this only true of the time of the work? Are models catching up on these kind of like specialized domains now, or?
I think they can use PubMed as their training data, so that could be much easier. But I think like still a lot of articles they are not publicly available. There are some copyright issues. So yeah.
Gotcha. Yeah. Thanks.
So another
can I ask one question? So I am surprised why the accuracy on in-domain goes down a little bit. Shouldn't it always go up here?
Yeah, because this goes down is compared to vision transformer. Those black box, they just rely on those confounding factors. They can cheat, taking shortcuts to achieve overly high performance. And our method, since we constrain the model's prediction using those knowledge priors, we cannot limit the model to just learn from the data. And this is a trade-off here. Like if you fully rely on the in-domain data, you can achieve very high performance. But if you constrain the model on the priors, it will drop a bit on the in-domain. But on average, across domains, we can achieve much better performance.
It would be nice to find a subset of the in-domain data where it goes up, a reasonable subset, because surely there is structure here that the prior is helping you predict, and VIT-based models without the prior, even if they use spurious features, if they're getting better answers, then they're getting better answers on some very corner cases in the data, surely not the entirety of it.
Yeah, I think we can answer that.
Yeah.
Thanks. So another application we published recently in Natural Communications is we apply concept bottlenecks to a very rare eye tumor. But it has very high death rate. And junior doctors has difficulties to classify such disease because it's so rare, they don't have enough experience. And we found we can use concept bottleneck models to help those doctors better diagnose those diseases. So concept bottleneck models will not only give you a final prediction, but also provide some other evidence like the top concepts. So it can get better user trust. So you can look at the concepts with the final prediction to make your own prediction. So we compare the performance of senior doctor, junior doctor, and junior doctors plus CBN. We found senior doctors can achieve very high performance. Juniors, their lack of experience, not comparable to senior, but when combined junior doctors with CBN, they can achieve close performance compared to senior doctors. Cool. So so far we talked about how to use language as model structure. And next, we will switch to the data, and we will show how to use language models to generate synthetic data to improve the data efficiency in embodied AI and vision language models. So we've seen great success of scaling language data from the internet, which we can train very good large language models. But it's still very challenging for some vision tasks. For example, like for this robotic transformer datasets, it took 17 months to only collect 130K episodes. Although we have relatively very large image text data like this line, 400 million, but the quality of those data is pretty low. Like the text data is mainly the alt text. You may be able to train vision language alignment model using those data, but if you want to build a more advanced vision language reasoning model, this data may not be sufficient. So we wonder whether we can leverage the textual knowledge we learn from text data to improve the data efficiency for those vision tasks. So in this line of work, we will show two papers. First is holodeck, where we use language models to generate 3D environments to train embodied agents. And second is a more recent work. I finished it after my proposal, which we try to use the coding ability of text-only language models to generate synthetic text-rich data to enhance visual language model. So let's start with holodeck. So holodeck try to address these challenges of existing data sets has limited scale and diversity. So, and they always rely on manual effort in designing those environments. So how can we automate this process? So we start with this motivation that those large language models, they contain the common sense or physical knowledge about how to design those environments. So the problem is, how can we convert those textual knowledge into interactive 3D environments? And to this end, we propose holodeck, which this system takes in language as input, like we want an office who is a professor who is a fan of Star Wars, and we can generate a interactive 3D environments with related objects in it. You can also put on your VR headset to navigate in those environments. Holodeck can generate diverse environments like arcade room, sculpture museum, spa, hunter cabin, etc. You can also customize the styles in those rooms. So with holodeck, we can have this exciting application that we can help the agent to generalize to novel environments. So we design those zero-shot object navigation tasks where the agent is required to navigate in a novel environments like music room to find an object like piano. So if the agent haven't trained on similar environments before or haven't seen such object before, they may struggle in those environments. However, you can prompt holodeck to synthesize those environments. Like we can generate synthetic music rooms to fine-tune the agent to perform better on those environments. So to validate this, we ask some 3D designers to build some testing environments. Like we have 10 novel environments across 5 categories. We use them as testing things. And we compute the performance of existing methods like Proxol, which is trained on 10,000 residential environments. But they just still achieve close to random performance. But with holodeck, you can achieve much higher performance because we can simulate or synthesize similar environments like those testing.
I think I asked you the same question during the proposal as well, but I've forgotten the answer, sorry. How do you manage to, after kind of figuring out which assets to put, etc., how do you manage to like scale them the right way, position them with the right poses, etc., etc.? Like how does all this happen?
Yeah, I think we have backup slides to explain in details, but basically we have a sequence is procedurally generated, like we generate the walls, the windows, and then find the related objects based on the user's input, and then arrange them with some spatial constraints, like sofa should be like facing to the TV stand.
And those constraints are also provided by the LLM? Or?
Yes, everything provided by LLM. But I think for now, I think nowadays those language models already have very good spatial information. We may no longer need to prompt it to generate constraints, but directly output the coordinates. So I believe this step can be simplified.
But the LLM does not know the coordinate system of the 3D asset that you're placing. Right?
Yeah, you just provide the bounding box of your 3D assets and maybe the boundaries of your room. Cool. You can output. Because it can draw like SVG, a lot of other stuff. So you should be able to learn.
Oh, so it's not just actually fetching assets and placing them, it's also like generating new assets of its own?
No, generate asset, you can rely on another more like a text to
Sure, okay, gotcha. I think
and are you also scaling the sizes of these assets, or are they fixed?
Those assets will be provided as context to large language models. So we will let them know, like we retrieve those assets, what's the size, 3D dimensions, and language models will rely on those information to provide a response.
Okay, but is there like a different sizes of the same chair? No.
Yeah, there could be, can you repeat the question?
In your database from where you're retrieving, there could be chairs of different sizes.
Yeah, we are retrieving from observers. We are retrieving from observers, which contains 50,000 So there will be a lot of chairs with different sizes.
It might also be worth if you say a couple of words about failure cases that you sometimes observed in object placement or things like that. Do you want to?
Yeah, I think in this holodeck system, we use spatial constraints to place objects. It works well for some simpler environments, but if you like generate a like a conference room or meeting room like the room we are in now, there are some iterative or like because there are so many chairs, so many tables. For those iterative or like some hierarchical arrangement, holodeck may struggle with that.
Okay.
Okay, thanks. So the last work I want to show today, which is done after my proposal, is to use code-guided generation to build text-rich data, which can be used to enhance visual language models. So the visual language model has been very popular recently, and which can process both image and text. And the architecture has been largely converged to this architecture. Like we rely on a retrained frozen language model, and we use an adapter to map the visual features into the textual space. However, such architecture has some problem, like it's extremely imbalanced. We always have a very large language module. So without high quality image text data to properly fine tune the model end to end, they may just ignore your image input and only rely on the language model to hallucinate an answer. So the open source community's lack of high quality multimodal data to train a visual language model. And a very critical application of such visual language model is to understand text and figure-rich images, like those figures tables we use in our paper and in many other fields. So it can help us to do some scientific literature research, help people with visual impairment, and also facilitate some exciting applications like digital agent. So there are some limitations for existing data sets. So first, they are sometimes unrealistic. They use randomly generated values and labels. So their lack of semantics. Second, their lack of diversity. They have limited types of figures. Like they only have like a bar plot or like line plot. And last, they have limited supervision. They only annotate with a short answer. However, to answer such questions, it requires multi-hop reasoning. If you only train your visual language model using those short answer only, it may just overfit to the answer biases in those datasets. So how can we overcome this challenge? So we start with this motivation that those text-rich images are usually generated from programs. So we use Python to generate charts, we use LaTeX to generate documents, we use HTML to render web pages. And we know that large language model has very good capability of generating code. So how about we just using language models to generate code, and then we can render them as our synthetic data. Another motivation or observation we found is the textual reasoning ability of large language models is still more advanced than the visual reasoning of those multimodal models. So we can show this by this evidence that we can use a text input of a table to ask language model to answer the question. We can render this table into an image to ask a visual language model to answer the same question. And we found on these wiki table question datasets, using text as input can achieve much higher performance. This highlights the gap between the reasoning ability across those two modalities. And we hope we can use the textual reasoning to enhance the visual reasoning. So our main idea is to use code as intermediate representation. So we can prompt a large language model to generate the code. We run the code to get the image data, and we use code as context to let language model to synthesize instruction tuning data like question and answers. And then we can use those multimodal data to fine-tune your visual language model to improve their performance. So we built this code-guided synthetic data generation system where the input is like a type of figure you want to generate, like I want to generate book cover, and output will be a multimodal data set with images and paired instruction tuning data. So here is the general workflow. Given the input, like generate book covers, we built 20 pipelines over the 11 tools we have. Like those tools could be like Matplotlib, LaTeX, or some specialized like SVG, HTML, etc. So for example, here we choose HTML, and it will start with topic generation just to get a general topic for this example. So here we use a persona-driven approach, which I will explain later, which try to diversify the topics we generated. Like here, like we generate select a persona of sci-fi novelist, will generate topics related to this persona. And then we have data generation to get more information or contents for the examples we want to generate. And then we can get the code. From code, we can render it into images. And using code as context, we can generate instruction tuning data like question and answers. So we use this persona-driven approach to enhance the diversity of our synthetic data. So we observed that language models have some biases. If you prompt it multiple times, it may give you similar output. So how can we control the diversity? So we use this persona-driven approach, which contains 200K personas. Each persona is like a one sentence to describe the personality or identity of a person. So we use this as extra input during prompting, and it will generate a topic related to this persona. Like here, like a sci-fi novelist, we can generate the images quite aligned with this persona. Here's another example, like we sample a persona of traveler, and can get a synthetic data related to this persona. Using this persona approach, we can just enhance the diversity of our synthetic data, and we use the.
Where do the personas come from in the first place?
So this is from an existing paper called Persona Hub. They just like crawling from the internet just to get a lot of information from the internet and summarize into one sentence about a person. Like they can get some information from Reddit or some other website.
And it's and the way the persona works in the end is that you just kind of like prompt this this LLM that's been fine-tuned on these personas with like a one sentence description of the kind of person you're trying to mimic, and then it'll output.
I think those personas were just used as an extra argument in the prompting stage, like just extra input. So we can just change the sample, random, like a random seed.
Yeah.
So we use this code-guided generation system to build a large-scale synthetic data set with 400K images, including chart data, documents like receipts or like a restaurant menu, have math problems, tables, diagrams, vector graphics, music sheets, electrical circuits, and even chemical structures. So to show those synthetic data can truly benefit vision language models, we start with this architecture, which is quite standard now, using Mistral 7B as the language backbone and Clip as the image encoder. So what we try to experiment here is during the supervised fine-tuning stage, we will include our synthetic data into this stage. So for the supervised fine-tuning data, we have different categories. So the first category is the evaluation data set. Those are the benchmarks we want to test the models. But they also have some training data we can use during the fine-tuning stage. We can have some auxiliary data sets. These are some other academic data sets they can use to just like to do some multitask training. And finally, we have our synthetic data. So our best performed model will use all those three categories of data sets, but we can also get a zero-shot model, which we do not use any training instances from the evaluation benchmarks. And for the baselines, we compare with some competitive open source models range from 7B to 12B, and also some proprietary models like GPT-4B and Gemini. And here is the main results. So we show the average performance on the 7 benchmarks, and we found our 7B model can achieve the best performance. We can outperform all the open source and closed models here. And more surprisingly, we found our zero-shot model, which do not using any training instances from those benchmarks, can outperform most of the closed source and open source models. This demonstrates that the models trained on those synthetic data can be well transferred to those real benchmarks. And to be noticed, most of those baselines, they are not zero-shot. They are using training samples.
What specific tasks is it an aggregate across many tasks? Like what specific tasks are these?
So we have chart QA, which is understand chart documents, is for documents like infographics or diagrams, a lot of text-rich benchmarks. Yes. Here are performance on each individual data sets. We found our 7B model can outperform GPT-4B consistently, and compared to the best numbers for each data set, we can achieve the best performance or be very competitive compared to the best numbers. And we did some applications to show the performance gain from our synthetic data. So we have different types of supervised fine-tuning data, like the auxiliary data sets, synthetic data set, and the evaluation training data. And so if we only use auxiliary data sets, this is a zero-shot model, but we found it has a significant gap compared to GPT-4B. Even we trained over 1 million images over those auxiliary data sets, but they cannot transfer to those testing benchmarks. However, only using synthetic data is still a zero-shot. We can get close to GPT-4B's performance, and this is purely zero-shot with only 400K images. And combine those two, our zero-shot model can outperform GPT-4B. Using supervised fine-tuning data, like from the training data of those evaluation benchmarks, it can outperform GPT-4B, but it's supervised. Adding auxiliary data sets didn't improve a lot, but adding our synthetic data, we can further boost the performance. And here are the breakdown performance on each data set. We found adding synthetic data, we can always improve the performance across all the data sets.
Yue, I think you said this, but I forgot. So synthetic data is used to fine-tune the clip and the text embedding at SFT time.
It's fine-tune end-to-end, fine-tune the language model, the connector, the vision backbone, everything.
Okay, so the full thing is fine-tuned.
Yeah.
Okay, thanks.
So one interesting application for our code-guided generation system is we can use it to bridge domain gaps to help it to generalize to some novel tasks. So given a novel task like answer a question about the nutrition facts, we can prompt our code-guided generation system to generate task-specific data. Like we can generate synthetic nutrition fact labels to train your vision language models to improve its performance for this novel task. To validate this, we built a small evaluation set called Nutrition QA with 100 examples. We just take photos in grocery stores and ask some questions. Some of them requires multi-hop reasoning. So we tested the performance of open source and proprietary models on this novel nutrition QA task. And this plot, the x-axis is the instruction tuning data size. The data size, which is the number of training samples they use during the supervised fine-tuning stage. And we found those models, they are not performing very well on this novel task, even they have already trained on huge amount of data. And a lot of those open source models, they claim they can outperform GPT-4B. But we found when testing on a novel case, when testing on like in the wild, GPT-4B is still very competitive. And those open source models, they are kind of overfit on the benchmarks. And our models, without using synthetic data, which achieve similar performance as those open source models. However, if we're only using our 400K synthetic data, we can outperform GPT-4B, or getting close performance to GPT-4B. And more surprisingly, we found since we can generate task-specific synthetic data, and using only 7,000 synthetic nutrition labels, we can achieve relatively high performance. And this is very data efficient. So from this experiment, we found those vision language models have limited generalization ability, and our synthetic data can bridge this gap. And another exciting application is we can let vision language models to answer with points. So like asking a question like point to the menu, those vision language models can provide the XY coordinates as an answer. So this can facilitate some exciting applications like web agent. And we found you can generate synthetic data for those pointing tasks. So how did we achieve this? We have the original code to generate those synthetic images like this restaurant menu. We can prompt a large language model to generate a pointing instruction, like pointing to the vegan options. And we can let language models to modify the code to explicitly draw the code, draw the point on the image. And we can just do some image processing to create a mask to extract the coordinates of those points. And then we can get those pointing annotations, and you can use those to fine-tune your reasoning. And we evaluate those pointing capability on this screen spot dataset, which contains some click prediction tasks on desktop screen and phone screens. And we compare with our baseline, which is pixel point. This is annotated by human with 150K images. We found our synthetic points with much smaller size of data, like 65K, we can achieve close to human annotated performance. And combine those two, we can achieve further higher performance, and it can outperform the SOTA method viewground, which is trained on over 1.3 million screenshots. And this demonstrates that synthetic data is a promising way to train vision language models to do pointing, and it is very data efficient. Any questions for this part?
Well, only 65K synthetic, does it asymptote there, or could you get continued gains if you generated an order of magnitude more synthetic data?
Yeah, I think that's a constraint from the cost and also because generating synthetic data is still, compared to human is much cheaper, but it's still time consuming and costly. Yeah, I think like in the future, like in the industry with more resources, we can try to scale this up. And in the paper, we have some scaling applications, which we show that scaling up to 100K can still improve performance, but it's getting saturated, probably because of the benchmarks. So to summarize, in this talk, we demonstrate two different ways of incorporating language bias. First, we use language as model structure using this bottleneck architecture. We can enhance the interpretability and robustness. And second, we can use language model to generate synthetic data, and we can enhance the data efficiency of vision language models and embodied data. So for the future, I want to keep exploring those two different directions. First, I want to build more trustworthy multimodal intelligence in critical domains. So we've seen great success in general domains. They can be very performant, but in critical domains, we need more properties of our system. Like we want it to be safe, to be robust. We want it to can incorporate knowledge, and we also want we can interact or debug with the model's behavior. And all those requires us to have better control over the system. And I believe we can obtain this through interpretable structure. And although in this talk, we only using interpretable structures for classification tasks, we also found such interpretable structure can help with some generative tasks. In our ECCVP paper last year, we used this explicit representation to encode human motions. We can encode the human motion into like the different body parts, the angle between legs and hands. Using these explicit representations, we can let language models to edit those concepts, and we can do some fine-grained editing. This gives us better controllability, and it is more likely to be deployed in some real cases. Another direction I want to explore in the future is previously we have built image classifiers which can perceive the world. Now we have vision language models can do some reasoning, but to make them those models really benefit the real world, we want them to act in some environments. And I want to build more generalizable multimodal intelligence that can interact with the real world. And first is I want to build multimodal digital assistant which can operate on our laptop or our phones to improve our productivity. And second, I want to build embodied agents that can reliably navigate in diverse environments to interact with our physical world. And I believe synthetic data is a promising way to achieve those goals. So in the last work for the VLM using synthetic data, we found we can use synthetic data to do pointing to monitor the click from action. Actually, we can synthesize the whole trajectory. Like given this high-level task, find hotels in Cancun, we can generate a sequence of those actions. All those images are generated by a large language model. We can use those synthetic trajectories to fine-tune your vision language models to do those web agent tasks. Synthetic data is also useful for robot manipulation. In our ICLE paper this year, we found we can use image or video as input for vision language models to generate digital twins of these objects, and is articulated. And we can train the embodied agent using those articulated objects, and it can be well transferred to the real world. Yeah, so I think I will start with the acknowledgement. I would like to first thank my two lovely advisors, Chris and Mark. So I met Chris in 2019. At that time, I was not sure what to do in the future with a mechanical background. And my only skill set is like 3D printing, soldering wires, and programming R2D2 robots. And Chris gave me opportunity to do research and always support every decision I made. Thank you, Chris. And I would like to thank Mark. Without Mark, my PhD journey won't be so smooth. And I will always treasure our memories. Like I sit in your office, we brainstorming ideas, we write papers together. We sometimes disagree with each other, and sometimes just share excitement. And thank you, Mark. And I would like to thank to my committee. Thank you, Dan, Dinesh, Pratik, and Jacob. Thank you for your valuable feedback and being so responsible to shape my thesis. I want to thank the whole UPenn NLP family, the Y Lab, CCP Lab, and many other labs. My PhD journey was never lonely because of you. And I would like to quote what Artemis said to me, to all of you. Like, we are not only research buddies, but we are also life partners. I would like to thank to all the other awesome collaborators for all the works presented in this thesis. Those friends are from AI2, UW, Stanford, and Penn. Thank you so much for your generous support and help. And finally, I want to thank to my family. Thank you to my parents and grandparents. They are not here in person, but I can feel their heart is with me at this moment, like all the other important moments of my life. Thank you, Mom. Thank you, Dad. And finally, I want to thank my partner, Chen Yu. Meeting with you is the best part of my life. Thank you for your patience listening to my random research ideas. Thank you for supporting me when I feel uncertain. Thank you for wiping my tears when I struggle. And thank you for sharing my joy when I success. And thank you for warming both my body and soul during many sleepless nights. Yeah, and I will leave time for question and answers.
Thank you, Yue. So let's move on to questions. I first want to ask if there are any questions from the audience.
I'll ask a question. So in the synthetic data works, it seemed like the language pairs you use really benefited from their expressivity to create like more diverse environments, or to like use them as like personas for prompts or code. I was wondering whether you think expressivity of language pairs can also help model structure building, maybe like with concepts that are like conjunctions, or even like making like a pseudo like decision tree or something.
Yeah, I think depends on the task, depends on what kind of property you want to improve over this task. Those interval structures, I think there are more constraints. They will limit models learned from the data, and you need to carefully monitor those trade-offs. But I believe in critical domains, it requires models to be more transparent and those interpretable structures, explicit representations will be useful in those cases.
Yeah, thanks, Yue. And any other question?
I have a question about noble. So some other works have shown that like if clinicians work together with the model, then they have worse performance than if we only use the model. Did you test like how like junior doctor plus concept bottleneck model compare with only using the concept bottleneck model?
Yeah, we have actual numbers in the paper, and we found if we combine junior doctors with black box, only provide a final prediction, we found they cannot improve model's performance. But when comparing concept bottleneck model versus doctors and plus concept bottleneck model, they don't have much difference. And they don't have much difference. But I guess even their performance difference is small, but the final decision is still made by doctors in this case. So I think like it's still a valuable tools to assist doctors in the diagnosis process.
I see. Thank you.
Okay, thanks. So let's move to the committee then. I mean, traditionally, we are going from the farthest to the local. So I guess, Jacob, you probably are the farthest. So why don't you take it?
Sure. So I guess maybe we can start with the first section, and this is sort of related to one of the questions that was asked before, but like you're getting a lot of mileage out of the fact that you have these kind of feature bottlenecks that you can just place a linear model on top of. And I'm curious what you imagine the generalization of that approach being to cases where the form of the predictor that you're trying to get is not linear, or where the knowledge that's contained in the language model is not just a list of features in terms of which you're going to be able to describe a linear predictor.
Can you repeat the question?
So, like, what do you do for classification problems where the form of the decision that you need to make in these sort of language bottleneck cases is not just a weighting of a bunch of features that, sort of a simple combination of a bunch of features that themselves have natural language descriptions?
Yeah, I think we in this paper we already show a lot of many more complicated tasks. Like I think like we apply this framework to diverse image classification tasks, and they always perform competitively with the black box models. So like from my observation, I think this linear combination is still very powerful tools. Like you can have a very comprehensive list of concepts, and those combinations can help you solve a lot of even very complicated tasks. And in some domains, we found models performance degrade, which is because the grounding functions like clip is not very reliable in those cases. Like chest X-rays, we need better grounding functions to guarantee models performance. So I think like if you want to ask like if those linear weights can just like solve a lot of tasks, I think like if you have very reliable knowledge priors, like those concepts are quite robust, and your grounding functions is pretty precise, I think it has strong potentials to apply in many cases.
Yeah, I guess what I'm trying to get at is like maybe one, do you have any examples in mind of cases where you don't think that basic recipe is going to work? And maybe the answer is no, and you think this is kind of everything you need. I mean, obviously, in the most extreme sense, if one of your features is just like solve the task, you can do that, but that doesn't seem, then you don't need this bottleneck at all. You can just go straight to the language model.
Yeah, I think this need to be evaluated more concretely. It's hard to say that doesn't work. It may have bigger gap with black box models in some tasks. And I think like it depends on different cases. Like in medical domains, we found this gap is mainly come from the grounding function, and also the knowledge priors. We can enhance those parts. But maybe in some other domains, those concept bottleneck models may not be expressive enough to solve this task. But yeah, I think we can further explore this in the future.
Mm-hmm. Okay, and then just very briefly about the second half. what you've presented are a bunch of recipes for doing synthetic data generation for a bunch of specific problems. And obviously these are all like super effective and the results you were presenting are very impressive. I'm curious whether there's some sort of like meta level knowledge you think we can extract here about how to do this in a general way so that, when we come to the n+1 domain or the n+1 task, you as the researcher don't have to say, okay, here's the pipeline that constructs the specific set of synthetic examples that we need for the specific sort of clicking task. And just what do you think the prospects are for even automating the design of those pipelines themselves?
Yeah, I think I can think about two high-level suggestions. First is we need to know what language models is good at. It's good at coding, good at some reasoning, math reasoning. So we need to first to see how can we transfer this kind of language models capability to a different capability. Like in this case here, we transfer the coding ability to some multimodal understanding. We need to leverage a good priors we learn from text data and apply it into a different task. We need to first verify if language models is good at some kind of use cases. And another thing is we found diversity is super important to guarantee the high performance. If you don't carefully design your framework, it may just yield repetitive or very redundant data. And you need to think about the mechanisms to increase the diversity. And in this work, we provide several methods, like using this persona-driven approach. And also our system can be controlled by text input. Like we can specify the type of data we want to generate, and you can just provide a very comprehensive input and to get a large-scale data sets. So those are good experience for future work to continue on building synthetic data.
Okay. Thank you.
Hey, thanks. So let's move on, Pratik.
Thank you so much for the seminar, Yue. This is really very excellent work. If one could crown you as the LLM whisperer, that I think you will deserve that title. I have the last part was new and it is very impressive, these results that we are looking at on this slide. I have maybe a slightly technical question, philosophical, I'm not quite sure, so let me say it. You are creating synthetic data by querying one LLM. This synthetic data is being used to train another transformer to do these tasks. So one has to ask, can we get rid of the second transformer? Specifically, if you think of few-shot learning, getting good answers on a query set is possible by creating a good support set or a good synthetic set in your language.
Yeah,
surely.
Continue. Yeah.
Yeah. So surely, once you're presented with a query set, you have a better understanding of what support set you would require. So the question to you is, should we imagine that creating synthetic data at inference time is going to be better than creating this kind of synthetic data in training a priori? Okay. And if so, how should we go about doing it?
Yeah, that's a good question. Yeah. So the reason why we use two transformers here is because we need a very powerful text-only language models in the first stage. It needs to be very good at coding, be very good at generating instruction tuning data, good at analyzing those numbers. And there are not good open source, like the open source vision language models now is not very good at coding. So that's the limitations we have now. Like if we in the future have a very good vision language models, which is also good at coding, we can design this kind of self-improve mechanism, like generating synthetic data during inference and use it to enhance its own performance. But at this moment, we still need to leverage a proprietary text-only language model, which is Cloud here, to generate those synthetic data. And then we can fine-tune an open source vision language model. But if in the future we can have a very powerful open source vision language model which can do code, I think this could be a very interesting direction.
So maybe if I interpret your response correctly, I'm a bit confused by the response because code generation and synthetic data generation, you are trying to argue that creating synthetic data is easier, better if you're good at code generation. And I am failing to see why such a tight connection between the two.
I think there are some confusing part here. I think like when we use the language models, we use it to generate code, generate data. We just render the code to create the synthetic data. So all those parts are done by a text-only language model like Cloud or GPT-4. And we're only using this data to fine-tune a multimodal model in the end. So I think code generation is a more challenging task, and there's no a good open source model that can do very good here. Maybe DeepSeek is doing pretty good here. So that's why we separate those two stages. We need to rely on a proprietary language model during the synthetic data generation. So the whole process of synthetic data generation is handled by one proprietary closed source language model.
But I think this is kind of like conflating 2 points, right? There's I think what Pratik was just to kind of riff off of what Pratik was saying. I think what Pratik was saying is you don't need to have distilled the synthetic data down into a model, whether it's a second model or a first model is a different point. And perhaps your answer was primarily focusing on whether that needs to be a downstream VLM that's consuming the synthetic data generated by an upstream LLM, right? But I think Pratik was saying you can actually be doing this at inference time. You could be at inference time provided with a new query, generating synthetic data to help you answer,
Yeah, I think that's another way to like, it's kind of like inference time scaling. Like we can, it's more like a tool using. So for example, like language models can using tools like Matplotlib to visualize some of the data. It may help you to better understand the input task. I think that there are some existing work using tool use to improve the performance on those like chart understanding, and it can improve performance in some cases.
So do you mind sharing some of your thoughts on the way people are doing tool use right now or reasoning right now? They're basically discovering new traces. There is no algorithm or there is no code being generated for the purpose of doing this multi-hop reasoning. If one wanted to build this system at inference time, do you think code generation is the way to go about this? Or do you think there may be a better way to create your restaurant menu?
Yeah, I think code has some nice features. Could be executable. You can get some feedbacks after running the code. It's very precise. I think we recently have a project which we try to use code as representation for those web agent tasks. So like you can always refer to the code as like a plan for your agent, and it's more robust than the like just a natural language channel sort of prompt, because code is like more concrete and precise. But there could be other ways. Like I remember there are some existing work using Sketchpad to draw something on the scratch paper to visualize something. It can help improve some performance on some math questions or geometry questions. I think it also depends on the task you try to improve. But overall, code could be a very general method during inference time.
Yeah, thanks. That's it from me.
Dinesh, why don't you continue?
Yeah. So I also wanted to ask a question about the last stuff, which was the newest, which is kind of related to what Pratik was asking about, but a slightly different question. Where it seemed to me like you went to great pains with these personas and then all of this stuff to try and reproduce something like the distribution of graphs that you might expect to be naturally in some sense naturally generated by humans, right? But that makes me wonder, would a simpler thing not have been that you start by looking at the graphs that do exist and anchor your distribution, your synthetic data distribution to those graphs in a kind of like much more, what would you call it? A domain randomization, data augmentation kind of way, right? Where you take this initial graph, then you parse it to see whether you're in fact actually regenerating the initial graph or something close to it. That gives you an anchor point that says, okay, here is a point in code that looks like what a human might have generated, and then you start kind of riffing off of that, right?
Yeah, that's a good idea. But I think we have some experiment in the paper we found. We compared to previous data set, which is just from some web. Our synthetic data is more diverse, much more diverse than those, because those websites, they may use some standard styles, like consistent styles when generate those figures. If you just crawl those data from the web, it may not be that diverse.
And in this case, you're talking about examples of like paired code and images that are found on these web pages. Yeah. But I guess you could mimic a much broader distribution, the distribution of the images that are seen. There's kind of like this analysis by synthesis kind of way of doing this, right? Like where you say, I'm going to use the fact that I know how to render code to then figure out what the right code was that generated this particular image that I found on the internet, right? And then kind of go from there. And do you have thoughts on kind of what the pros or cons of, because it can't be that you're kind of getting, my guess is that there's always going to be some kind of distribution mismatch, regardless of what you do to manually prompt this LLM in all these, like, with all these personas, et cetera, et cetera. There's always going to be some distribution mismatch with what the distribution of human generated images looks like, right?
Yeah, I think the pros is such method, if you rely on anchor on some real distributions, it may be more realistic, and the statistics or information you get is like more reliable compared to what we did. Like everything synthetic, you may just have some like unrealistic distributions. So that's the pro, and the cons is you may still encounter some privacy or copyright issues if you look at some of the data on the internet. But in our case, like everything synthetic, we don't have such concerns. And also like the cons is like you complicate the process. Like you need to find what are the target distributions, what are the websites I can refer to. It will make the whole process more complicated. In our case, it's pretty simple. Like you just provide input, like I want bar chart, I want pie chart. It will output a diverse data sets for you. So it's more easier to scale up.
Yeah, in your case, the upstream LLM already trained on all the copyrighted data for you. Okay, so there was a point where you said I kind of asked this question in the middle of the concept bottlenecks part, and there was a point where you said that the auto-generated concept bottlenecks actually work better than the manually listed attributes for birds, right? And that got me thinking, why should we expect this to be the case? Why is a carefully curated data set of bird features, and birders are notoriously they're very particular about these things. Why would that not be sufficient to distinguish birds in the same way as these auto-generated things? What does it mean to come up with a good bottleneck? What does it mean to come up with a good concept bottleneck?
Yeah, there are a couple of reasons. If you look at those bird data set and their attributes, they are not natural language. They are more like the head color, column, black. It's more like structured or like those attributes.
But that's a superficial thing, right? Surely that can be corrected, right?
Yeah. And that's related to another problem is the grounding function, where we use clip to connect natural language and an image. But if we're using those not very natural language, and also their differences is pretty small. Like the head color, it will be like bird color, head color red, head color white. If you compute the clip similarity, so there are one word difference. So like the grounding part may be a problem. That's one part. Another thing is the comprehensiveness of the bottleneck, because we can generate much larger bottlenecks. It can contain more types of concepts. It will improve the expressiveness of your system compared to human annotated, which they will just like have like maybe 100, less than 100. It will largely restrict all those capabilities. It's too much constraints. but ours is more flexible.
Are larger bottlenecks in general better always?
Yeah, it will be better, but there's also another trade-off here is for the interpretability. If you like have like 10,000, 100,000 concepts, it's hard for human to interpret it. So there's a trade-off. Always like bigger bottleneck improve.
Yeah, this also kind of like leads on to another question that was in my mind. There's been now a lot of work on concept bottlenecks since the original paper in 2020, right? And maybe there's already work in this vein, I'm not aware of it, but I wonder if, this principle of avoiding shortcuts using these concept bottlenecks, if the lossy abstraction of a concept bottleneck is just too high a price to pay for avoiding spurious bottlenecks, maybe we should be indeed using something like concept bottlenecks to first avoid the shortcut, but then slowly kind of start to relax that so that you can actually add some much less easy to capture in language, like much more tacit kind of knowledge in your system.
Yeah, I think I have seen such works to avoid models taking shortcut using concept bottleneck models. So they will add residual layers.
Okay.
So model they will check if they rely too much on the residual layer and to determine whether I should add or delete these concepts. Until the importance of the residual layer is pretty low, we can delete that residual layer. So the final model will not rely on spurious correlation, but rather on those interpretable concepts. So that's
Gotcha. Yeah. Okay. One, if I still have time for maybe like one kind of philosophical question, which is kind of a question that you've had some time to think about, because I think we asked a very similar question in your proposal. When is synthetic data the right way to use the priors from LLMs, and when is it instead capacity constraining the downstream model? Because these are both, like you said at the beginning, these are both ways to think about priors. The first is a very kind of natural way to think about priors. You're constraining the function class, right, by constraining the bottlenecks. The other is a way to say, okay, I'm going to use as large a function class as I want, but I'll just make sure that it can't overfit by creating a really, really expansive data set, right? And so are these effectively the same thing at some point? Are they, what is the right way to think about when to use them?
Yeah, I think in this thesis, we kind of separate them because they are quite different tasks. We have different objectives. But I think in the future, they can be converged in some point. Like we can build interpretable structures and also train them on synthetic data. I think that's doable, but we currently do not have very good, because nowadays, like the tasks people are interested in are like generative tasks, and we haven't found very good interpretable structures for those kind of tasks. If we can find such architecture in the future, we can train those interpretable models using synthetic data, and we can achieve a better world for both sides.
Yeah, thank you.